welcome to the first video on proof, and in this video we're going to go through a whole heap of definitions. So it's going to be fairly text heavy, fairly labour intensive, but we need these definitions so that we can have a conversation about how mathematicians actually prove results. So the first thing we need to know is what we mean by a statement. Now a statement is something that there isn't a fixed recipe for. It can look different in different contexts, but what's always going to be the case is that a statement has to be either true or false. It needs to be written in a way that it can be either true or false, and it can't be both at the same time. That doesn't mean it's always true and it's always false. It can change its value, but it can only be one of them at once. So here's a really simple example. N is a prime number. This is a statement. It's either true or it's false. But n can change its value, so therefore sometimes it might be true, sometimes it might be false, but it can't be both at the same time. So if we choose n equals 3, for instance, then it's clearly a prime and the statement would be true. But if we chose n equals 8, that's a composite number, the statement would be false. So it can change its value depending on what the context is, but it can't be both at the same time. Okay, now we know what a statement is. What do we mean by a proven statement, and what do we mean by a proof? So as I've said, some statements can change their logical value, whereas others, they're always true or they're always false. And if we can establish that a statement is always true, then we've proven the result. We've proven that statement. And the method that we use, the steps that we took to establish that, is called the proof. So here's another simple example. 17 is a prime number. This time the number's fixed, so this statement is going to be true or it's false. This one can't change its logical value. It's either going to be true or false. 17 is either going to be a prime number or it's not a prime number. And we can establish, in fact, it is a prime number simply by just listing the first few prime numbers, and we see that 17 is on that list. There's our proof. Okay, sometimes it is sufficient to prove a statement true by looking at every possible example and assessing whether those examples are true or not. And that's what we're saying here. Unfortunately, most statements are sufficiently complex that there's just too many examples to test all of them. And therefore, it's not feasible for most statements to go through and prove every single example is true, and therefore the statement's true. We're going to have to come up with some other techniques. What is true though, and this is kind of similar to the sciences as well, a single counterexample is enough to prove a statement false. Okay, so here's another simple example of this where we can actually go through the examples because it is a simple enough statement. So here we're saying that every odd prime less than 20 either has a remainder of 1 or 3 when divided by 4. So there's not many odd primes less than 20, there's only a few of them, so we could easily go through and divide each of them by 4 and assess what the remainder is. And if we do that, then we see that in fact the statement's true. They all have either a remainder of 1 or 3, and then hence we've proven the statement by using examples. But as I said, in the real world, this is probably not going to happen. There's going to be way too many examples for us to work on, so we're going to have to come up with some other ways of generalizing. Here's an example of where a single counterexample is enough though. So every integer is even. Now there's an infinite number of integers, so there's no way we could go through every single example and assess whether this statement's true. But thankfully, one counterexample is enough to prove this statement false. 3 is an integer. It's not even, therefore the statement's false. Okay, now we can move on to negation. So negation switches the logical value of a statement. It usually will use the word not, but I couldn't help myself with this next sentence. Not all negations use the word not. And we will see some examples of that a bit later, and I'll point them out when we get there. Now we're going to find with mathematics, there's kind of two foundations that build up all of modern mathematics. One of them is set theory, and the other one's propositional logic, which is what we're learning about now. You should have seen set theory in year 9 and 10 and the advanced course, and you probably saw it somewhat in extension 1 as well if you've done combinatorics. So set theory is something you should be familiar with. What we're going to try and do is tie in propositional logic interset theory so that we can see they're both very much related and they're kind of the critical foundations of all of modern mathematics. And for us here in particular with a negation is very much related to the idea of a complementary set. So here's a simple example. Here's a statement, today is Saturday. It's either going to be true or false. The negation of that is today is not Saturday. Here's another example. All square numbers are even. The negation of this would be not all square numbers are even. And hopefully you can see the original statement, all square numbers are even, is false. And here's a perfect example of where we can use something other than the word not to create a negation. Now, not all square numbers are even, that's a negation, but we could, from our understanding of English, reword that as some square numbers are even. Okay, so let's start bringing in some notation and very much try and show the correspondence with set notation. So the first thing is we're going to find working with statements easier if we kind of bring in some algebra. So we can actually, you're used to working with algebra, pronumerals to represent numbers. In fact, we can go far more abstract than that and we can represent whole statements here by a pronumeral. Often we'll use P for a first choice, P for proposition, the thing that we're proposing to be true. Here's a boring example. Let P be the statement, all horses are mammals. So if we were working through a problem here, trying to establish whether this was true or false, then whenever we saw the pronumeral P, that's representing that sentence, that statement, all horses are mammals. Okay, now when we're working with statements, we can look for a correspondence with certain words and our understanding of sets. Now, in set theory, you would have probably already talked about the idea of unions and intersections and their relationships to the words and or, and we're just stating that here. And then we've already said that negations are related to complementary sets, and you'll often see these two symbols down here, either this one or this little tilde symbol here. They're going to represent the word not, and they're associated with complementary sets. Okay, now in the language of set notation, we mean this. If I'm talking about two statements S and T, that's going to be related to the intersection of S and T. If I say S or T, that's going to be related to the union of S and T. And if I say not S, which I'm using the symbol for not here, not S, that's equal to the complementary set of S, or the complement of S. What we want to do is see if we can further refine this relationship and look at what's the negation of F and T. And I'm saying there, what's the complement of the intersection of F and T, and what's the negation of F or T, and what's the relationship to the complement of F or T. Now this is easiest to see by way of an example. So we're going to consider the set of Fibonacci numbers, which we're going to call F, on a standard six-sided die, and the set of triangular numbers on the same die are represented by T. Okay, so here's a Venn diagram of the six numbers on a standard die, and we've split them up via the Venn diagram into groups. So the Fibonacci numbers on the die are 1, 2, 3, 5, the triangular numbers are 1, 3, 6, and poor old 4 is not in either of them. So it's sitting in the rectangle, but it's not in the circles. Then it's easy enough to find the intersection of F and T. That's the bit in the middle that's in both the F circle and the T circle, and that's the numbers 1 and 3. And we're using our standard set notation here. Okay, then it's easy enough to find the complement of that. It's all the bits that currently aren't coloured in. So not F and T is going to be the bits that weren't coloured in, so that's going to be the numbers 2, 4, 5, 6. Okay, that's easy enough to find. And what we would really like to see is if this was as simple as working with our complex numbers. When we were looking at conjugates, we said that the conjugate of two complex numbers, like P plus Q, would just be the complement of P plus the complement of Q. We could just break it up. That would be great if we could do that here. What's the complement of F intersect T? We'd love it if it was just the complement of F intersect complement of T. So we're going to see whether that's in fact true. So if we look at that, then we can see that the complement of f is 4 and 6. That's the numbers that aren't in the f circle. The complement of t is 2, 4, 5, the numbers that aren't in the t circle. And therefore the numbers that appear in both of those sets, unfortunately, is just the number 4. It's just the outside of the circle. And that doesn't match with what we coloured in for the complement of f intersect t. So unfortunately, it's not as simple as this case here. And that's what we're saying here, that they're not equal. Unfortunately, we can't just simply break this apart like we were hoping, but hopefully there's still a simple enough rule that we can work with. And in fact there is. It's actually complement of f union the complement of t, and you could go through and establish that that was in fact true. Look back through the last few slides and see that those two would actually match up nicely. So it is still simple, or it can be broken apart, but it switches the symbol. So instead of being an intersect, it becomes a union. And it works the same way for the complement of f union t. It breaks it apart, but it switches the sign to an intersect. And these are called De Morgan's laws, and they're incredibly important, of course. So there is still a simple rule, but it's not quite as simple as we were hoping. Okay, now we need to talk about another critically important definition, and it's called an implication. So an implication is a relationship between two statements, and it's such that the second statement directly follows as a logical consequence of the first statement. So it is a directed thing. It has a specific direction to it, and we normally can write an implication, reword it into the form if this then that. So that is a logical consequence of this. Okay, and again, to bring it back in terms of sets, we can think of these as subsets. Okay, and we can introduce this new double arrow kind of symbol here, and again it has a direction to it. So here's an example. Consider the integers less than 20, and we're going to say that the set O represents the odd numbers and the set M represents the numbers that are one more than a multiple of 4. So the odd numbers, easy enough to write down as a set, there they are, and the set M, the numbers one more than a multiple of 4. Well, remember 0 is a multiple of 4, so add 1 to it, you get 1. The next multiple is 4, add 1 to it, you get 5, then 8, add 1 to it, you get 9, and so on. So we've got our set O, we've got our set M. Then clearly, looking at those two sets, I can say that M is a subset of O. And remember my symbolism for subset. M is a subset of O. Subsets are also directional. And you can see that it's a subset because everything in M occurs in O. But there are numbers in O, it's a proper subset. There's numbers in O that aren't in M. So M is actually smaller, a smaller piece of O. So it's in fact a proper subset. Okay, and then this is where the implication comes in. I can word that then, since I know that anything in M is also in O, I can write that down. If a number is one more than a multiple of 4, then it is an odd number. So there's my implication. Okay, and hopefully you can see why the implication works the way it does. That if I'm a multiple of 4, I'm in that smaller set, I have to be in the bigger set. There's no choice. And that's why we've got this logical consequence happening. If I'm a number one more than a multiple of 4, I have to be in that set of odd numbers. I don't have a choice. Okay, another important thing that we can talk about are quantifiers. So quantifiers are words such as sum or all. They're the most common things that we use, and they represent a quantity. They tell us how much of something we've got. Do we have all of it, or do we have some of it? And you'll often hear the synonym there exists used as well as an alternative to some. So we can introduce some notation. You'll see this upside down A symbol, and that's going to represent for all, or all things that we're talking about. And we'll see this backwards E shape, and that's going to represent there exists. Okay, so here's an example of what I mean by that, using it sparingly. Just because we can doesn't mean we should. Okay, so in this example, I'm saying you should be able to read this, and when you get practice, you better be able to read it, but it doesn't mean you should jump in and use it. And you're probably, if you're going to see it at all, it'll be in a multiple choice question at the beginning of the test, just to assess, do you know these symbols? So here's a crazy example of a statement written with these symbols. And you can see it looks quite daunting until you get used to reading them. So let's try and unpack it. Okay, when we unpack it in simple English, if you can see here, this says for all m in z, for all m in the integers, there exists a k in the integers, such that 2m plus 1 all squared is equal to 4k plus 1. Well, let's unpack what that actually says. It's saying for all m, and here we're saying 2m plus 1, that's an odd number, and we're squaring it. So for all odd square numbers, we're saying there exists a k, and this is one more than a multiple of 1. So we're saying that all odd square numbers are one more than a multiple of 4. And that's what we're saying here. So it looks scary, but we should be able to unpack it with practice so we can see what it actually says. Okay, continuing on with our implications. We've said that an implication can be written in the form if this, then that. The this and that have important meanings. And we're saying here two new things, sufficient and necessary conditions. Well, that if this then that statement, we're saying that the if part, the this part, that's the sufficient condition. The second part, the then part, that's the necessary condition. So here's an example. If a number on a die is prime, then it is a Fibonacci number. And if we write down those two sets, the prime numbers on a die 2, 3, 5, the Fibonacci numbers 1, 2, 3, 5, then we're saying it's sufficient to know that a number on a die is prime to guarantee it's a Fibonacci number. And if we have a look, if I know that a number is prime on the die, then it has to be 2, 3, or 5, and they are all Fibonacci numbers. So if I know a number on a die is prime, I'm guaranteed that it's a Fibonacci number. That's what's sufficient. That's what a sufficient condition means. Okay. Whereas being a Fibonacci numbers, we say it's necessary to be a Fibonacci number to be a prime, but it doesn't guarantee it because we could be that number 1. Okay. So we have to be in this list to be a possible chance of being a prime number, but we might not be. And we keep bringing up for implications the idea of subsets. If we're in the smaller set, we're guaranteed to be in the bigger set, but if we're in the bigger set, we might not be in the smaller set. Okay, converse statements and equivalent statements. A converse statement, basically we've talked about the idea that an implication says if this then that. The converse statement is that in reverse. So if we have if P then Q, the converse statement would be if Q then P. So we've kind of flipped the P and the Q around. And unfortunately, they could have different logical values. Just because if this then that, just because if P then Q is true, that doesn't mean that if Q then P is also true. It'd be great if it was, but unfortunately it's not always the case. So often in maths we have to prove try and prove both directions, and sometimes we'll find one direction works and not the other. Now, two statements are said to be equivalent if they both imply the other. In other words, if the originals and the converse are both true. And we can extend our implication symbol to this more important and powerful case of equivalence by using the double-headed arrow here. Because remember we said implication has a direction. Well, here we're saying they both imply each other, so that the arrows are pointing in both directions here. So an example of that, a quadrilateral is a rhombus if and only if it has 4 equal sides. So you often see equivalence written in that way, if and only if. That's saying that the implications are running both directions. As you can see here, I can split it into those two if this then that statements. Quadrilateral is a rhombus, it has 4 equal sides. If a quadrilateral has 4 equal sides, then it's a rhombus. Works both directions. In equivalent statements, then the pieces are both sufficient and necessary. Okay, critically important idea for proof is called the contrapositive. So we've said we've talked about a statement and its converse, if P then Q, and the converse is if Q then P, and we've said they don't necessarily have the same logical value. The contrapositive of a statement will have the same logical value. So if we have a statement if P then Q, the contrapositive is if not Q, then not P. Okay, and these two statements are logically equivalent. So sometimes it's easier to work with the contrapositive than it is to work with the original statement. And if we can prove the contrapositive, then we get the original statement being true for free, which is nice. So here's an example. Consider the statement, if I own an Aston Martin DB9, then I own a car. The contrapositive to that is if I don't own a car, then I don't own an Aston Martin DB9. Okay, and clearly you can see from this that they are in fact logically equivalent. And there's our work on definitions done.